guys, welcome back to another Waves and Vibrations problem. Simple harmonic motion 3. A 0.60 kilogram mass vibrates according to the equation x equals 0.45 cos 6.40 t, where x is in meters and t is in seconds. Determine A, the amplitude, B, the frequency, C, the total energy, and D, the kinetic energy and potential energies when x equals 0.30 meters. So a bit of theory before we start this problem. The general form for simple harmonic motion is given in terms of the trig functions sine and cosine, which I have here. X is the position of the spring at a certain point. So x equals a cosine omega t or x equals a sine omega t. Now, let's just go through what the variables mean first. X is the position of the spring. A is the amplitude. W is the angular frequency, and t is the amount of time that has elapsed. Now, whether or not you choose cosine or sine depends on the conditions upon which the formula is going to be made. For example, if you are starting the data collection when the spring is at the maximum amplitude, in other words, you stretch the spring and then you let go, then you're going with a cosine omega t. If you're measuring the data based on after you let go, the spring goes through its equilibrium position and then back through again, you're going to start with a sine, because sine, when time is 0, the amplitude or the distance moved is 0. Okay, so in this case we're dealing with cosine. It's already given to us, so we're going to just work based off that. And actually the first few parts of this question are very straightforward. Okay, so for example, part A, we're asked to find the amplitude, right? And based on this formula, amplitude is the number that precedes cosine. So in our equation, it would be 0.45. Okay, so A is equal to 0.45 meters. Okay, and that's it. Part B, we're looking for the frequency. Okay, now frequency is F, okay? In the equation, we're given omega, this W symbol, the angular frequency. Now the relationship between angular frequency and F is this. Okay, so since angular frequency is equal to 2 pi F, solving for F, divide both sides by 2 pi. F is equal to omega over 2 pi. And we know omega. Omega is the number that precedes the t, also in the argument of cosine. Okay, so here it would be 6.40. So here we go. 6.40, the units are seconds to the minus 1 over 2 pi. And when you punch that in your calculator, you are going to get 1.019 hertz. Seconds to the minus 1 is the same thing as a hertz. And because, let's see, we've got 3 sig figs here used in our calculation, so we can only express our answer to 3 sig figs. So therefore, we can say that frequency is approximately 1.02 hertz. So there's the answer for B. All right, moving forward, part C, the total energy. Okay, so to find the total energy, you got to think about this for a minute. Hey, when a spring is moving back and forth, there's various energies that are exchanged in between. Okay, so let's say this is the spring at its unstretched length. Okay, you then stretch it and you let go, right? So let's say there's a mass at the end, for example. You stretch it, you let go, it's going to go back through its equilibrium position, and it's going to have some compression there, and then it's going to go back through this, back to this, here and back. So, you know, it's going to go through a few different stages. The idea is this. At any point in its motion, you can find a total energy. But here's the thing. Let's say you chose this point right here, or any point in between these three, rather. Any point in between these three, there's a combination of kinetic energy and elastic potential energy. And here's the thing. The equation for elastic potential energy is 1/2 kx squared, k being the spring constant. We don't have that. So finding the total energy through this means is going to be difficult. We know that kinetic energy is 1/2 mv squared. Now here's the thing. We can try to find speed or given the mass, so that's not a problem. There's other ways that we can find those values. But can we find a spot where the total energy of the system is just kinetic? And the answer is yes. Okay, so when the spring is fully stretched out to its max, you're holding it there. It's not moving. It has 0 kinetic energy. It has pure spring energy. Same here at its maximum compression. It's not moving at that instant. So it's 0 kinetic energy, fully spring energy. However, at that point, at its equilibrium point, let's say you stretch it and it starts collapsing back on itself, as it passes through this equilibrium point before compressing, it has purely kinetic energy, because at this point the spring is in its equilibrium state at that very small amount of time. So there is no elastic energy. And the reason for that is the compression X goes to 0 because it's at its normal length. So this disappears and you're left with 1/2 mv squared. So the idea is this. We're going to work with this based on the fact that at the point where it passes through its equilibrium position, the total energy is 1/2 mv squared. But bear in mind also, you know how I said here the speed is 0 and here the speed is 0? That means at this point here, the speed is at its max. So this is a 1/2 mv max squared. Okay, now, how do we get Vmax? That's the next part. Okay, how do we find Vmax? Well, just like we do in other physics problems, how do we usually find the speed? Okay, think back to your original kinematics formulas. Speed is equal to distance over time. The only difference is in this case, we're looking for maximum speed, and it's not linear, it's simple harmonic motion. Okay, now here's the thing. In simple harmonic motion, the distance you travel d, it's equivalent to a revolving object making a complete revolution. Okay, and when you undergo a revolution, you're undergoing circular motion. Okay, so the distance you travel in a circle is a circumference given by 2 pi r. Now, what's the radius of this motion? Well, it's the amplitude of the motion, right? Look at this. You're extending the spring out, it goes back to equilibrium, compress, come back to equilibrium, expand, equilibrium, compress, equilibrium, out. And this cycle repeats itself over and over. This maximum distance here is the amplitude. And when it compresses to its max again, that's the amplitude. Anything in between, we call that x. That's where the formula comes from. Okay, so it's a cyclical motion. Okay, so this can be modeled by circular motion or rotational motion. Okay, so that's why the distance undergone is the same as that of an object undergoing revolving motion. Okay, so 2 pi r, in this case the radius of that cyclical motion is the amplitude, you can see that here, divided by t. Okay, so the time to undergo one revolution is called a period, and it's given the special symbol capital T. Okay, so 2 pi a over capital T. Now one more substitution. We know that frequency is equal to 1 over period. Okay, so instead of having 1 over period here, we're going to substitute frequency in, so 2 pi AF. Now, I'm going to rewrite that as 2 pi FA. And the reason for that is because, hopefully you recognize this, 2 pi F is omega, the angular frequency. So I can actually simplify this even more and call it omega A. Okay, so in other words, I've just stated that the maximum speed is equivalent to the expression omega A. And this is what I'm going to plug back in over here. Okay, so now we still have 1/2 m. Now it's omega A squared. Okay, so there you have it. At this point, I just want to plug in my values. So 1/2 mass is 0.60 kilograms. Omega is based on the formula 6.40. And we've got our amplitude 0.45. Those two numbers multiply together, then it gets squared, multiply by 0.6, divide by 2, and you're going to get 2.488 joules. Now, for the values we used in these calculations, we use the 0.45 and the 6.40. And because 0.45 is only significant to two significant figures, we're going to use this value. So we're going to round this to 2 sig figs. It's going to become 2.5. So E total equals 2.5 joules. Okay, so there you go. Finally, we've got one more part to this problem. We've got part D. Okay, the kinetic and potential energies when x equals 0.3 meters. Now, you know that the maximum extension is 0.45, which means 0.3 occurs somewhere in between, not at the maximum amplitude A. So at those points, we're going to have a mixture of spring and kinetic. So now you realize we actually do have to know K, so we're going to have to be a little creative in how we figure it out or how we substitute it out. Okay, so let's find the kinetic and potential energies when x equals 0.3 meters. Okay, let's start with the potential energy first. Potential energy. Okay, so potential energy, we stated earlier, was 1/2 kx squared. But the problem is, well, we don't know k, so how do we find it? So we should be a little bit creative when we do this. So if you look back to video 132, we saw that, so recall, the frequency of a spring is given by the following formula. F is equal to 1/2 pi times square root of k over m. K being the spring constant, m is the mass. Okay, now let's try to solve for k here because we know the mass, we know the frequency, so we can figure it out from this formula. So first things first, multiply the 2 pi over, and you get 2 pi f equals square root of k over m. 2 pi f, that's the same thing as omega. So omega is equal to root k over m. Square both sides. Omega squared equals k over m, and finally multiply both sides by m. So then k is equal to omega squared m. So we're going to use this and we're going to plug it in over here. Okay, so now we've got ES equals 1/2 m omega squared x squared. And we know all of these things, so at this point you just have to plug it in your formula and crunch the numbers. So 1/2 times 0.60 times 6.40 squared times 0.30 squared. And when you punch that in your calculator, you are going to get approximately 1.111 joules. And again, because we're using certain values in our calculations, we're only going to round this to 2 sig figs. So this is going to become approximately 1.1 joules. So there's the potential energy when x is equal to 0.3. Now for the kinetic energy. So at first glance, you might think, I can't figure that out because I need to know the speed, right? 1/2 mv squared. Sure, I can find the max speed, but how do I find the speed at a certain point? Well, the quick and easy answer is you actually don't need to know it, and that's because earlier in part C, we found the total energy, and that we might have used the maximum speed point to calculate that, but that is true for any point in the spring's motion. It may be comprised of different energies at different parts or different ratios of the energies, but the total number of joules stays the same. So therefore, kinetic energy, we can say that EK is equal to E total minus ES. It's the difference, right? That's all it is. So the total energy being 2.5 joules, the potential 1.1 joules, and you're going to end up with 1.4 joules as the difference. And that's it for this video, guys. I hope you enjoyed it. Be sure to smash that like button if you did, and subscribe to Physics in the Flesh so you catch my latest videos, which I post every weekday at 12 noon. Stay tuned tomorrow at 12 noon for video 134, Simple Harmonic Motion 4. What? Wait, who's back to school? Pumpkin pie recipe. Okay, I'll save that for Halloween. Guys, so that's it for this video. I hope you enjoyed it. If you did, be sure to smash that like button and subscribe to Physics in the Flesh so you never miss a video from me, which, by the way, I post every weekday at 12 noon. So be sure to be on my channel at that time. Guys, as always, if you missed my videos from the past, be sure to click over there on the right. You'll see some of my latest videos there. And other than that, guys, I hope you enjoy the rest of your day. Peace.